It's time for another episode of Math on the Sphere. Episode 1, Math on the what? Hello and welcome to Math on the Sphere. My goal with this series is to make spherical math as approachable and intuitive as the flat plane math you may already know. I'm going to show you the whys as well as the whats and hows so that you'll understand the topic more deeply. As a result, you'll have more fun and better success in the subjects of geometry and trigonometry. You'll also gain some valuable intuition for 3D visualization. Some of you may be wondering what exactly is spherical math. Spherical math deals with lines and shapes as they exist on the surface of a sphere, rather than on a flat plane. When you first studied geography, you learned that the Earth is round, and you discovered that portraying any sizable portion of it on a flat map introduces distortion. Perhaps you remember the first time you compared a world globe to the more familiar wall map, and how different this experience was. Spherical math allows you to deal with the metrics of this situation with the same precision as you would on a flat plane. To capture the essence of this point, there's a classic riddle, which you may have heard before. A bear hunter walks 1 mile due south, then he turns and heads due east for 1 mile. He turns again and proceeds another 1 mile due north, only to find himself right back where he started when he notices a bear. What color is the bear? Why? We can think about this and remember our compass directions, which I'll draw here: north, south, east, and west. In our most natural way of two-dimensional thinking, we're applying these directions on a flat plane. The hunter starts out and heads 1 mile south, then 1 mile due east, and finally 1 mile due north. How can this be? It looks like his path is an open loop, so how could the hunter possibly be back at the same place he started? Well, this highlights the limitation of thinking about travel in terms of a flat plane. We know the world is round, and if we consider the compass directions on a spherical Earth, we see that we have a different situation. On our spherical Earth, north heads toward the pole, toward this, our North Pole here. South heads away from it, and east and west follow these circular paths, which get shorter and shorter as you get closer to the pole. If Santa were to build a house, or let's say his workshop, right over the North Pole, then all 4 of its walls would be facing south. Now picture this. Looking downward from directly above the North Pole, that just a mile southward from the pole, you have an east-west path that's a small circle, just over 6¼ miles long. If you start at the pole and head south for a mile, you reach the circle. Then, it doesn't matter how far you go east or west along that circle, as far as the riddle goes, you'd still be on it. Wherever you end up on the circle, when you turn north and go 1 mile, you're back at the pole, right where you started. So now you can see that this riddle works when the hunter starts at the North Pole, and the answer is, the bear is white, because it's a polar bear. I really hope these bears don't go extinct, by the way they're dying off now, so that we'll be able to keep this riddle alive for generations to come. We'll come back to this riddle again in a later episode. It turns out the North Pole isn't the only location that works. Now imagine you're a pilot getting ready to fly a plane from San Francisco to Moscow. You want to proceed along the shortest possible route, so you need to know which way to head, and you'd like to know how far you'll be going. This is spherical trigonometry in action. If you know the precise latitudes and longitudes of both places, their angles relative to the Earth's equator and poles, then the problem boils down to just solving a spherical triangle. You might at first think that this triangle on a sphere is much harder to visualize and figure out, but it's really only a little bit trickier. The beauty in this topic is that it's not all that different from solving a plane triangle, a much easier problem to visualize intuitively. In this series, we're going to review how to solve any triangle on a flat plane, and then we'll expand that understanding to handle spherical triangles. After that, we'll spend some time developing a better intuition for how geometry on the sphere works out, more generally. The history of this material is quite rich and interesting in its own right. In ancient times, some 2,000 years ago, the Greeks were concerned with navigation, but they were even more concerned with observing the sky, the moon, the planets, the stars, and especially the sun. The sun's path across the local sky held the secrets to day and night, summer and winter, and all that goes with that. Figuring out exactly where any very distant object will be located in the sky at a given place and time is another spherical problem, with the sphere's surface representing all the different directions an observer, located at its very center, can look outward. In medieval times, 1,000 years ago or so, Islamic astronomers in the Middle East and India practiced and refined this math with great vigor. They were concerned with two things: determining prayer times from the motion of the sun across the local sky, and facing properly for prayer from wherever they were, directly toward the city of Mecca. The knowledge spread to Europe and became all the more important during the age of exploration, starting about 500 years ago. Once we began sailing across oceans, and then, about 100 years ago, flying around the world, navigation became the critical application. The math was developed in a more fundamental and formalized way in Scotland 400 years ago, when the triangle became the key functional element. Aside from some refinements introduced around 200 to 150 years ago, the subject has remained mostly complete and unchanged ever since. They used to teach spherical geometry widely in high school, back when sea and air navigation were more of a manual undertaking. Today, it's covered in just a few specialized niches: astronomy, crystallography, satellite telecommunications, and of course, navigation. Still, I hold that studying the topic is well worth the effort. I've formulated this math in a new way that is much easier to approach and remember, which I'll be sharing over the course of this series. So let's move on to the next video and get started.